Okay, actually I'm just realizing that some of these might not work because I just canceled it, but okay, we'll get to that problem when we get there. Okay, so I already installed the packages, so I will go through and load for the Jonquerie test, which I didn't end up doing. Descriptive statistics, post hocs, and graphs. So this week for my question, I was investigating self-esteem levels of employees versus power strategies used by supervisors. So the tests included 30 participants, 15 in the group where the supervisor used hard strategies, and 15 in the category where they used soft strategies. So the levels of self-esteem were measured on a scale of 1 to 30 at the beginning or the end of day 1, and then where the supervisor started using the tactics, and then following a week of treatment. So I will input the data using the factor variable power, and I will indicate 2 levels of treatment, so the hard and soft, and this command will create the variable power containing 2 blocks, so the treatments of 15 rows of participants. The next column will have the values for the dependent variables. Self-esteem measured the week before treatment, so that's the day of the first day, and then post-treatment. So these are the before treatment scores. These are the post-treatment scores. So lastly, I just have to combine the 3 variables that I made into a data frame, which I named ES data, so esteem data. Okay, so the Wilcoxon rank sum, as we talked about, is like the independent t-test. So in order to do this, we want to run descriptive statistics for the data. So we want to split the power. So we want to see the hard and soft. And we're going to use these to see if the distribution is different than a normal distribution. And we also will be looking at the Levene's test to also see if there are group differences and test for homogeneity of variance. So, oops, I already installed that. Sorry. And library that. Oh boy, hope this works. Okay. So we're going to run it for the before data and for the post-treatment data. Okay, so we can see that for the before treatment data, oops, sorry, for the Shapiro books. So this is for hard power style and soft power style before. So our p-value is 0.08 for the hard and 0.17 for the soft. So we can say that for the before treatment data, the distribution for the hard power style and soft power style are normal, and so we can tell this by whether the significance of the Shapiro-Wilks test, which we ran, is less than 0.05 or is greater than 0.05. So it was greater, non-significant. And then for the post-treatment data, the data for the hard power style are non-normal, 0.01, and then 0.02. And so this finding would mean that the sampling distribution might also be non-normal for the hard and soft condition data for the post-treatment group, and that a non-parametric test should be used. And we use these to check for homogeneity of variance, and both of them are above 0.05, so we can assume homogeneity of variance. Okay. So to actually run the Wilcoxon test, we need to create a new model for each condition, so the before treatment and the post treatment, and indicate the outcome measure by BES and PES. The group, which is from power, the data set. Exact is false because our sample size is less than 40, and correct equals false because we want to get the approximation of P and get rid of continuity correction. And then after this, we will run each model, take the results. Okay. So from these results, we can see with the p-value that type of power style did not significantly affect self-esteem levels after the first day of treatment. So this is the before. But the power style did significantly affect self-esteem levels a week after treatment, so 0.002. So we were told, I don't remember if we had to do this on here, but I did for this test, walking it through, and I think it was one of the like Jane Super Brain things. So to rank the data, you want to use the self-esteem scores for the before treatment group in the hard condition first. Create a new variable. For the soft condition, and then you determine the number of people. You indicate the number of people in each group. And then you convert those to ranks. You're using all of the variables from before. You split the ranks into two different groups. Find the sum of the ranks and correct for the number of people we found above. And then you can rename the groups and run, get the totals, and then calculate the mean rank for each group. So 16.9 and 14.1 for the hard and soft. Okay, and we also can do that in Excel. That's just a faster way to get the totals. Okay, so next we are going to get the effect sizes from the models we created earlier. And then we will enter the model name and the sample size to get the effect sizes of each group. So the output for the effect sizes shows that the R values are negative 0.16 for the before treatment and negative 0.57 for post-treatment. So that represents a small effect for the before treatment because it's below 0.13, and which is technically medium effect, and then a large effect for the post-treatment data because the effect size is above 0.5. I also did the Wilcoxon signed rank, didn't read through the directions, so I created a new model. I used the same data, but since it's the dependent t-test kind of version for non-parametrics, I just used the same participants and pretended to compare the difference in scores between the conditions. So using the data from above, I will find the difference between the self-esteem scores in the before treatment and after treatment for the hard and soft groups. So created a new model that represents the difference between the self-esteem scores in the before and post-treatment conditions. Got the descriptive statistics. And then had to split the data frame into the two different groups. and then had to do the same as above, created the new model for each group. And then finally run to get the outputs of the Wilcoxon signed rank. Okay, so we can see that we have a normal distribution for the hard group, p-value is 0.942 in the change scores, and for the soft group, the difference scores are approximately normal as well at 0.252. So we don't need to use a non-parametric test for either group, but we are going to anyways, which I already did. So we want to run the analysis on the hard and soft groups separately, so we split them, and we will use the same function that we did for the Wilcoxon ranked sum, but we want to tell R that the paired is true because the data are paired, so the dependent groups, it's the same person. So we can see that for the hard power condition, the self-esteem level, this is for hard, was significantly higher after the first day of treatment than after a week of treatment. And, oh, I have to run the effect sizes, sorry. And then for soft power conditions, the self-esteem levels were lower after the first day of treatment than after a week of treatment. Okay, so next I did Friedman's ANOVA. So I already already imported the data set from Excel. And I ranked the data for each person. So starting with the lowest 1, 2, 3. So I have another grid on my Excel sheet where I did that for all of those. And I created R was doing something weird, so I just created a new model with each of the conditions, so I called that time. So the 1 week, 3 months, and 6 months, just to run my tests. So once again, we're going to get the descriptive statistics for the conditions. And we want to see if the data deviate from normality, indicated by the p-value. So the p-value is down here. And none of mine did. All of them are greater than 0.05. Oh, and this was, yeah, I ranked my groups in Excel. So I had to library reshape to run the ANOVA and the post-hoax. So we will run the Friedman test with that and get the chi-squared, the degrees of freedom, and the significance value. So all indicated right here. And then we will run the post-hoax tests. So, and from these we can say if the column says true, then the groups differ significantly, but if it says false, then they don't. So job satisfaction of the participants did significantly change over the first 6 months of employment, indicated by the p-value. And the post-hoc tests were used with the Bofferoni, which reminds me of Boiardi, I don't know why, and Bofferoni. And it appears that job satisfaction did not significantly change from the first. Oh, I didn't even talk about. Sorry, I didn't even talk about my data. This was job satisfaction 1 week after starting a new job, 3 months, and 6 months. That would be helpful. So The job satisfaction of the participant significantly changed over the first 6 months of employment. So we said that in the Friedman rank sum. So our p-value. And then the post-hoc test used with the Bofferoni correction applied with it revealed that job satisfaction didn't significantly change from the first week, so false, of employment to 3 months. So my first one was first week, then this was 3 months. But from the start of employment to 6 months, so first week to 6 months, and from 3 months to 6 months, they did. And in all cases, the critical difference corrected at alpha 0.05 for the number of tests was 10.7. Okay, bye.